Hi everyone, welcome to the exercise class. I think we can start slowly. So in today's exercise class, I'm going to discuss the exercise sheet which was posted this week. And two main points that come up there and which are also were present in the previous lecture are the topic of energy preservation of a system under some transformations given a particular Hamiltonian which describes the system, and also a notion of the temperature of a qubit. So we'll first briefly talk about these two things, and then we can see if you have any questions, and let's see how it goes. Okay, so let us start with energy preservation. So what I mean here by energy preservation is, suppose that we have a system, and then there are two things that that can happen to a system, right? So first, the system is described by Hamiltonian H, and then we can apply some transformations to the system, which is governed by this Hamiltonian. So, and these operations which we perform on a system are described as a unitary. So we just label it as a unitary U. And what we are interested in is this particular class of unitaries which do not change the energy of the system irrespective of the initial state of the system. So we're looking at class of unitaries such that our U preserves the energy of the system, irrespective of the initial state. And the statement that we can make here is that if U and H commute, which means that UH equals HU, then we can state with certainty that the transformation U does not change the energy of the system, which is governed by Hamiltonian H. And it doesn't matter which state of the system is initially in. So why is this true? So first, let us remind ourselves what is the energy of the system. The energy of system is essentially the expectation value of the Hamiltonian. So if we assume that the initial state of the system is rho, then the energy of the system in the initial state is just a trace of h rho. Then suppose that we apply a unitary U and evolve the system, and the state of the system after this transformation, let us label it as rho prime, and rho prime is just U, rho, U dagger. So the energy of the system after the transformation is a trace of H, rho prime, which is trace of H, U, rho, U dagger. Here we can use the fact that H and U commute. Then we see that this is just UH rho U dagger. And now we use the cyclic property of trace. So it's trace U dagger U H rho. And because U is a unitary, U dagger is equal to identity. So we are left with trace H rho, so our initial energy. Hence, we can see that if H and U commute, then the energy is conserved irrespectively of the initial state of the system rho. Of course, one can also see, and we'll look at the particular example of this, is that some unitaries, even though they don't commute with the Hamiltonian, can conserve the energy of the system for a particular initial state. But to look at it in more detail, let us consider a particular example. So suppose that we're looking at the 4-level system with the basis states that we label as 0, 1, 2, and 3. So it's a 4-level system. Okay, and let us consider following Hamiltonian H, which we'll write in this basis of 0, 1, 2, 3. So this 0, 1, 2, 3 basis is basis in which Hamiltonian is diagonal, essentially. So, and the Hamiltonian as follows. It's delta 1, 1 plus delta 2, 2 plus 2 delta 3, 3. So in the matrix form, we can just write it as only having these diagonal terms. We see that this Hamiltonian is so this Hamiltonian is degenerate because there are two basis states, 1 and 2, which correspond to the same energy delta. Okay, and now let us think let us look at the examples of what the energy preserving unitaries are. So what would be an energy preserving unitary, which is non-trivial? So here we can actually utilize the fact that indeed the levels 1 and 2 have the same energy delta. So the states 1 and 2 have the same energy delta, which means that like if we compose our unitary such that it would just exchange these two states, then or map state 1 to 2 and state 2 to 1, then then like even intuitively we can see that the total energy of the system should not change because we're just operating between the two states which have the same energy anyway. So then we can write such a unitary which would preserve the energy. So it would exchange between the states 1 and 2 and 2 and 1. And for the states 3 and 0, it would just keep them in place. And in the matrix form, this unitary would look like as this. And one can also check that indeed this unitary would commute with a Hamiltonian. Okay, so now let us look at the example of a non-trivial unitary which would not preserve the energy of the system. So for example, here one can also use the fact that the states 0 and 3 have different energies. So the state 0 has energy 0, and then the state 3 has energy 2 delta. which means that if we exchange between these two states, in the case, of course, when their populations are different, then the total energy of the system will change. So, as an example of such a non-preserving unitary, would be if we exchange the between states 0 and 3. And also 3 and 0 because we need our operation to be unitary. And for the states 1 and 2, we can just keep them in place. In the matrix form, this will correspond to the following. Okay, and so for this non-preserving, for this unitary, which does not preserve the energy, in a general case, so we can check that U non-preserving and H actually do not commute. However, if we look at the structure of this unitary, which does not preserve energy for an arbitrary state, we can see that for some states it would preserve the energy, because, for example, if the initial state of the system is just the state 1, then this unitary just maps its state to 1, and the initial energy of 1 would be delta, and it would be mapped to 1, the energy of which is also delta, so the total energy of the system would not change. So even if we have a unitary which does not commute with a Hamiltonian, for particular states, it can still preserve the energy. So I'll just add it as a comment. Yeah, this is also in this case like actually true for any state which is superposition of the states 1 and 2. Okay, so this was about the energy preservation. Now let us go to to the next topic, which was introduced in a lecture, and which is very important for understanding how thermodynamics are modeled in a quantum world. And this is a concept of a temperature of a qubit. So the idea of what we understand as a temperature of a qubit is pretty simple. So suppose that we are given a qubit, which is the state of which is just described by a 2x2 density matrix, right? So states 2x2 matrix. And the idea is that like we can always find a particular basis in which this matrix is diagonal. So we find a basis in which it's diagonal, so we diagonalize the matrix. And so we end up with a diagonal matrix, and any diagonal matrix can be written down as a thermal state for some temperature. So as you remember, we were looking at the thermal state in a previous exercise class, and we can and now we want to use it for a particular case of two-level system. So suppose that we have a qubit, and it is a two-level system, right? So if we look at the Hamiltonian, which governs such a system, the states of which we label as 0 and 1, we can imagine that there is some energy difference between the energies of these two states. And we can write the Hamiltonian as just as delta 1, 1. From the first exercise sheet, you should know that. So one of the things that you should have taken from the first exercise sheet is that actually we can always assume the energy of the ground state to be equal to 0, and because this constant shift in a Hamiltonian only corresponds to some global phase in the final solution. So we can always write the Hamiltonian of two-level system in such a way. And then if we look at the thermal state for some temperature T, for the system with such a Hamiltonian, then we can write it as follows, where Z is just the normalization factor. And here we also, as we will always do in this course, label 1 over KT as beta. So now let us write this in the, so let me write this first with a beta. So in the matrix form, in the basis in which the Hamiltonian is diagonal, so in this case it's just our 1, 0 basis, this will just look like as a diagonal matrix. So here I'm just writing a normalization factor, and the entries on the diagonal would be 1 and e to the power minus beta delta. Okay, so, and because the thermal state for two-level system looks like this, we can see that actually, like, if we have an arbitrary state which is diagonal, we can always find a beta such that it would correspond to the thermal state, characterized by this temperature beta. So to consider some examples, so the first example, suppose that we have a state, pure state, rho 0, 0, 0. So to find beta, which corresponds to this state, we just need to find a beta such that 1 over 1 plus e to the power minus beta delta equals 1, or approaches 1 as beta approaches its value. So this means that e to the power minus beta delta should approach 0, which means that beta has to approach plus infinity. So if we choose beta equaling plus infinity, then essentially we will get our ground state. So physically, what this means is one can note that if we choose beta equaling plus infinity, or tending to plus infinity, then if we remember that beta equals 1 over kt, this means that t then has to approach 0 from the positive side of the real axis. And essentially remembering our analogy with our thermodynamic analogy also with the Gibbs distribution, we can see that indeed if the temperature in which we consider the system is tending to 0, then the population the population of the system will concentrate in the ground state, because the system simply wouldn't have any energy to jump to the excited state, which is here the state 1. Okay, so then if we take a second example, let's call it rho 1, also a pure state, but now it's 1. Then to find a corresponding beta, we just need to find beta such that 1/1 plus e to the power minus beta delta equals 0, because this is just corresponds to the matrix 0, 0, 0, 1. Which means that e to the power minus beta delta has to tend to plus infinity, which means that beta has to tend to minus infinity. So which means that if we choose beta equaling minus infinity, then this would correspond to the qubit in a state 1. And finally, the last example that we can take, let's call it row 2. We can now look at the maximally mixed state of a qubit. So 1/2 0, 0 plus 1/2 1, 1, which would just be this density matrix. So here, to find an appropriate beta, we just need to find beta such that 1/1 plus e to the power minus beta delta equals 1/2, which means that e to the power minus beta delta equals 1, beta equals 0. Okay, so and then what we can also do, we can just put the states on the beta axis. So for beta equals 0, this corresponds to the maximally mixed state. Beta minus infinity corresponds to the state 1, 1, and beta plus infinity corresponds to the state 0, 0. And here we can already intuitively see, or directly see, why choosing beta, it might be a better option for discussing populations of states instead of talking about the temperature, because we see that these populations of states are continuous in beta, but you can show that they would not be continuous in 1 over k. They would not be continuous in t, because you would have a problem when you would be approaching 0 from the negative side of the real axis and from the positive side of the real axis. Like, these two limits would not converge to the same thing. Okay, so better to use beta to ensure the continuity in populations. And okay, so, and this is how we introduce the notion of the temperature of a qubit. Of course, this notion applies to can be applied to any two-level system which is described as two levels having some difference in energy. So as soon as you can kind of introduce this non-degenerate two-level system, then immediately you can also introduce this concept of temperature. Yeah, so this applies for two real qubits. This also applies to virtual qubits, where you just choose two levels of two states of different energy in a more, possibly a system with more degrees of freedom, and there you just introduce the virtual temperature between these two particular levels.